Our third finalist, all the way from Australia, NBN Company.
Thank you. I'm Joe Forbes. I'm part of the operations research team working on the deployment of the National Broadband Network in Australia. Thank you for your time today. We're excited to talk about how operations research is being used to help reduce the cost to design and build the Australian National Broadband, the NBN project. Specifically, we will show how operations research will reduce construction cost by at least 10% and design cost by 80%. To be clear, that is a 2.2 billion Australian dollar saving on a 20 billion component of an overall $36 billion project. A project that is the largest national infrastructure project in Australian history. During this presentation, we will provide an overview of the NBN project, describe the design and construction problems NBN Co faced, explain the operations research solution that was developed to address these problems, and describe how we created FOND, Fibre Optic Network Design tool, to deliver the solution. And then we will highlight the impact of the solution. The two companies involved in the design optimisation projects are NBN Co and Biarri. NBN Co is a government-owned company. It was established by the federal government to build and operate a wholesale national high-speed broadband network. Biarri is an Australian commercial mathematics company that was established to help business efficiently use their resources. Biarri provides custom optimisation solutions to deliver the power of mathematics to enterprise. In 2011, NBN produced a series of videos to describe their plans for the network. The next video introduces the Australian National Broadband Network.
The internet plays an increasingly crucial role in our lives, which is why a new broadband network is being rolled out across Australia. It's called the National Broadband Network, and it has the potential to transform how we learn, have fun, work, and how we stay in touch with those we love, even how we visit the doctor. It's about striving to change how some Australian companies do business with the world. In the past 10 years, the amount Australians download from the internet has exploded, up 19,000%, and it'll continue to grow. By 2015, the average internet-connected household is expected to generate almost 6 times the traffic they did in 2010. Our existing infrastructure is getting on, so NBN Co will roll out newer, faster fibre optic cable. Over the next 10 years, we'll be deploying over 200,000 kilometres of the stuff. And at peak rollout, we plan to be hooking up 6,000 homes a day. But it's not just about fast internet. It's about giving 100% of Australian premises access to broadband. 93% of premises will connect to the network through fibre, while smaller communities and hard-to-reach locations will receive satellite or fixed wireless technologies. We're working with Telstra to access their existing ducts, which means less digging for us. However, if it is necessary to dig up the verge in front of your house, we'll put it right. We'll even take a photo to ensure we get it right. The National Broadband Network is wholesale only. This means you'll still buy your telephone and internet services from the same providers you know, giving many Australians new options, and your service provider will organise getting your house connected to the NBN. NBN Co is investing in the future of Australia, creating an asset that we expect will pay its way, deliver a return for taxpayers, and build a network that our kids and grandkids can benefit from. This is a nation-building project, and it's already begun. It's not just a whole lot of fibre. It's about creating new opportunities for every Australian. The National Broadband Network, bringing broadband to life.
The next speaker is Peter Ferris, the Executive General Manager, Planning and Design, who will talk about the scope and challenges of the project.
Thanks, Joe. G'day. My name is Peter Ferris, and I'm the Executive General Manager of Planning Design for the National Broadband Network in Australia. I really would like to be with you guys today, but unfortunately I've just had a multi-level laminectomy on my lumbar spine, and that severely reduced my mobility, so I can't get around as much as I'd love to. So, to the problem itself. I was fortunate enough to join NBN Co at a very early stage in 2009, where I had the challenge of putting a plan together of how to provide connectivity for 10 million premises right across Australia. Now, Australia itself, while we may only have 22 million people in the country, the land area of Australia is roughly the same size as the continental US. So we had a very big challenge to actually provide this connectivity. We looked through the different options that were available, and the determination that we had was to provide the broadband access for consumer, business and industry was to provide fibre for 93% and a combination of terrestrial wireless and satellite for the remaining 7%. The land area occupied by the 93% of dwellings or premises is only around about 6% of the land area. The majority of the Australian population are located in the 5 capital cities, and the remainder of it is spread out right across Australia. So how did we go about determining which areas to connect with fibre? We started off by looking at the towns with more than 1,000 dwellings or premises within those towns. We then provided a transit network to connect all of those together with 121 aggregation nodes where the retail service providers would access those services. We then looked at towns that were within about 20 kilometres of that transit network, and any of them that were over 500 premises, we connected those as well. So the majority of the premises in Australia were going to be fibre connected. We then needed to determine how could we connect these 1,000 different locations to the fibre network itself. So we had 1,000 fibre access nodes that were the central points for them. We located those within the Telstra central offices or exchange buildings, and out of those we provided a distribution cable and a network of what we called fibre serving area modules. A fibre serving area module, or FSAM, is a collection of 16 fibre distribution areas. These are about 200 premises around a fibre distribution hub that allowed connectivity from what we called our local cables up to our distribution cable and then back into the fibre access node itself. The fibre serving area modules are the cornerstone of our design elements. They are what we contract out to build, and they are what we had as our design element. So we had about 3,000 of these to design over a 9-year period. Now my challenge was how am I going to get these 3,000 designs completed by engineers who love to put their own personalities into designs, and I needed to have them done in the most cost-effective way, in a consistent way, right across the network, right across Australia. We also had to minimise the disruption to the community. So in order to do that, we had to maximise the use of the existing infrastructure. We had a deal that we'd set up with Telstra, Australia's incumbent telecommunications industry, and that deal gave us access to 130,000 kilometres of duct, and that access was on a take or pay. So we really had an incentive to utilise that duct. We also had deals with the existing energy distributors, and we could access the aerial infrastructure as well. So we had a combination of aerial infrastructure on poles, we had the existing Telstra duct, and we had new civil build, and we had to put those together in an optimised design structure. Now, we started out with our 5 first release sites doing this manually with a range of different design companies in Australia doing designs for 5 sites that we could then start off with and get to know how these technologies was working. While I was going around Australia presenting the design parameters that we had in our design philosophy to the industry, a guy come up to me in Brisbane, actually Joe, and told me about a mathematical modelling solution that would actually give me this consistency in design. As an engineer myself, I wanted proof. So what we did was we actually took the existing first release sites and compared a design that was done manually by these different design companies with what FON could produce. And we found quite amazing savings in the civil build activity, the amount of material that was used in each of these areas. That allowed me to take that to my CEO at the time, who was Mike Quigley, who I was incredibly fortunate to have as a CEO because he actually got it. He understood the maths. And so he supported us in going ahead with Biarri and starting on our journey to continually build and refine FOND as our design solution.
I'm Paul Kennedy, the CEO of Biarri Networks. I'll explain how we characterised the problem Peter faced. First, there is the issue of quantity. Peter needed to process 2 designs a day for 9 years beginning in 2011. These designs needed to be produced shortly before construction was scheduled to commence. This was to ensure feedback from the field could refine the architecture definition. The second issue is intricacy. This is understood by inspecting a completed design. Shown here are the land parcels to be served. On these are placed cabinets in blue and a distribution ring in purple. Around each cabinet is a local cable in 2 tiers. The first tier comprises large cables, shown in dark blue, terminating at splice enclosures, hollow circles and red circles. The second tier comprises small 12 fibre cables and multiports, green lines and hollow stars. Finally, each premise is connected using a single fibre cable and a premise connection device. A completed design can consist of up to 7,000 elements as shown here. In the past, a fibre planner had to create each one of these by hand. The design has to be exhaustive, every premise connected, no more, no less. The design has to be geometrically correct as it will interact with existing infrastructure. The design must be fully named and typed as it will be used to inform the construction. Finally, the design must be fully associated, nodes are connected to arcs and vice versa, to simplify downstream analysis. The last issue is complexity. In each of the design, there are 4 primary decisions which could be made for each node and arc. They're presented here sequentially, but in reality are made simultaneously. The first is whether to install aerially or underground, or a hybrid. Peter mentioned the Telstra agreement, which gave him access to the huge set of Telstra duct. The cost of installing cables in existing duct cost $10 per metre. In comparison, aerial installation will cost $25 per metre. However, the duct and aerial network are incomplete and overlap, so some new build is required. Building new duct, then installing cables, increases the cost to $110 per metre. To compound the issue, there is typically a limit to the number of cables allowed on an aerial span, so new duct may be required beneath the span. The component choice affects this decision. The duct running down a street may be capacitated and so only holds smaller cables. One design option is to run a small cable in from either end, both terminating in the middle. This will increase the total cable length, but will avoid the installation of new duct. Finally, there is the question of where to place joints or splice enclosures. These are sized according to the cables they connect. The pits or vaults that house these are capacity constrained and have different sizes, so a suitably sized pit may be in the wrong place and so require additional cable out and back. Peter faced 3 issues: quantity, intricacy and complexity. Our solution used mixed integer programs embedded in our software product FOND, Fibre Optic Network Design. FOND is used by over 50 planners at NBN Co. Michael Forbes will explain how FOND solves a series of interdependent MIP models to produce a network design.
Good morning. I'm Michael Forbes and I'm an optimisation expert at Biarri. We'll use a schematic diagram of the network architecture to explain the optimisation tools used to design the network, working from the exchange towards the premise. The total area served by an exchange is known as a fibre service area. The exchanges are connected to each other by the National Transit or backbone network. For the most part, the National Transit network already exists, though it does need to be augmented to build in redundancy, establish points of interconnect with retailers, and to carry the anticipated increased data. Each exchange serves several areas known as Fibre Service Area Modules, or FSAMs. As explained by Peter, FSAMs are the fundamental building block of the network and consist of approximately 2,500 to 3,000 premises. From the exchange, a distribution ring connects to all cabinets or fibre distribution hubs, FDHs, then back to the exchange. This part of the network must be underground to minimise the possibility of damage and consequent disruption to the service. The area served by an FDH is known as a fibre distribution area and consists of around 200 premises. Premises in very close proximity to each other are grouped together and connected to the same multiport. A multiport is a small device connected near a fibre optic cable which allows individual fibres to be removed from the cable and then connected to 1 or to 12 service drop cables which each connect to a premise. Design criteria may require more fibres to be connected from the cable to the multiport than there are premises in order to allow for network growth. Multiports are connected by local cables back to the fibre distribution hub. The network within a fibre distribution area is usually a tree. As well as the demand and the design criteria, another critical input for the optimisation tools in FOND is the candidate network. Which arcs may be used in the network construction. This typically consists of existing Telstra ducts with their known capacities, existing above-ground networks for electricity or existing telecommunications infrastructure, and street centreline data to represent the possibility of building new underground networks. Design rules determine when much less expensive above-ground arcs are acceptable. The overall optimisation challenge is to produce the minimum cost network for an FSAM subject to the design constraints. After searching the literature, NBN Co and Biarri determined there was no available algorithm to optimise an entire FSAM. So Biarri developed a series of optimisation tools which, when used together, produce a very high quality solution for an FSAM. These tools are broadly speaking used in the following order. The actual process is considerably iterative for many practical reasons. So the first tool is the multiport hub selection tool. This groups individual premises into multiports within an FSAM. This is solved using a hub selection mixed integer program to determine how each house ultimately connects to the network. Each of these hubs is quite small, say 4 to 6 premises, and their placement and connections are dependent on local infrastructure. In underground networks, we consider the option of remediating pits, actual holes in the ground, so more multiports can fit into the pit. A cable length constraints means there are few choices at this level, and experience suggests that there are minimal global optimality losses as a result of the decisions made at this level. Indeed, it was only late in the development of FOND that this became an optimisation step instead of just an automation step. Overall, the aggregation process at this level reduces the demand nodes from around 3,000 premises to approximately 650 multiports, vastly simplifying the next step in the process. The next step is the FDH hub selection, positioning the FDHs within an FSAM. This is done using a hub selection mixed integer program. The candidate location sets for these hubs is quite restrictive as placement is subject to local council approval. This tool and each of the tools allows for user intervention after it is completed. This allows planners to make small changes based on details unique to the area which are not easily conveyed in an automated way. The next tool builds a distribution ring. The distribution ring connects all the FDHs to the exchange. And the distribution ring is built using dedicated underground cabling. This problem is solved using a specialised MIP which is similar to some travelling salesman or vehicle routing problem formulations. The ring can have one branch, and for reliability purposes the path between any pair of FDHs must share no arcs with any other path between a pair of FDHs, subject to it being possible to go down both sides of a street. The next optimiser is the FSAM detailed solve. This key optimisation is run to connect all multiports to FDHs. This optimisation can use spare capacity in the distribution ring to save on cost. This tool simplifies some of the architectural rules without compromising the feasibility of the proposed solutions. The optimisation is based on a MIP model which can be run with or without pre-specified FDH locations and with or without a pre-specified distribution ring. When it is run with a large collection of potential FDH locations, it can replace the FDH hub selection tool. However, given the tight restrictions on FDH locations and the impact that has on runtimes, this is not often done at NBN Co. Mathematically, this problem corresponds to partitioning the FSAM into a set of capacitated trees, each centred at an FDH, in order to minimise the construction cost. In this tool, we use a number of specialised integer programming techniques to achieve the detailed solve. Special branching variables are introduced relating to the underlying trees. It turns out it's enough to build undirected trees rather than directed trees. So we added high priority branching variables that represent if a node is a potential branching point in the tree, a hub or otherwise, and if an arc is included in either direction. This modelling technique, which was key in the development, reduced run times from around 12 hours to 2 minutes. We can also deploy a number of MIP-based heuristics. We can run to integrality on the branching variables, which are then fixed, and then the other variables are resolved to integrality. We can add extra candidate hub locations in a rolling fashion. A final cable allocation optimisation is run to allocate specific cable types to each part of the network. The difference in cost of cable types is at least an order of magnitude smaller than cable installation costs, and so it is ignored in earlier optimisations. While the design rules are intended to drive consistency, there are occasions when they need to be broken. Examples of design rules we might rarely but sometimes like to break include rules such as never cross a train line or never exceed 200 metres for certain cable types. FOND enables consideration of these options to be done in an objective manner. Let's hear how Luke Birch, Senior Fibre Planner at NBN Co, used FOND to evaluate options when faced with a scenario where the design rules needed to be broken.
One of the FSAMs that I've had that's quite tricky was a Gosford FSAM. It was a long, thin FSAM and it was bound by a water body and a mountain range, so it was quite complicated to carve up manually. I used FOND to design the FSAM and I had about 15 variations which I chose the most optimised design out of. Each variation took about 5 minutes to run.
So how well does FOND do? In 2010, NBN Co commissioned an initial bake-off comparing FOND to expert, Grand Master if you like, manual designers across 5 sites. These sites were chosen to be representative of the different residential areas in Australia, though the areas on the left of this diagram are more common, represent more areas than those on the right. For each of the sites, 2 manual designs were produced. The results were here compare the best manual design for each pair to the FOND design. The savings were very significant, particularly in the areas of reduction in new underground network and the reduction in the number of cabinets or hubs. If we look in detail at an area in Townsville, the purple lines here represent the distribution ring, the green lines represent the local network, and the red rimmed lines represent new underground builds required for the local network. If we compare this manual design to the FOND design, just watch carefully, we see a very significant reduction in the new underground ducts required for the local network, a reduction in the red rimmed lines. If we look at the figures, we then see that the very large reduction in the trenched FDA figure, the trenched local network, has led to an overall cost reduction in excess of 10%. Another bake-off was conducted in 2012. Again, the cost savings were very significant. Perhaps more important were some of the soft issues. In one area, FOND required new underground network in only 4 contiguous segments, whereas the manual solution required 57 new underground segments. In 2 areas, the manual designers had used non-standard equipment, very large hubs, which significantly increases the chances of error when building the network. And perhaps most tellingly, in one area, the manual designers produced an infeasible design. It would not have been able to be built. If we drill down into one of these areas, we see the locations of hubs represented as squares, the outline of the FDAs, the hub areas, in blue, and the distribution ring in green. The manual designer has built a very complex distribution ring in order to reuse the existing duct network as much as possible. However, in doing that, they have increased the number of hubs required and not considered what new underground network will be required for the fibre distribution areas themselves, the local network. FOND's solution is both much simpler and significantly cheaper. At the end of these bake-offs, NBN Co determined that FOND would save at least 10% on construction costs compared to the best manual designers and up to 20% compared to average manual designers. One of the key benefits of FOND is the capacity to consider architectural alternatives which will emerge over a 10-year project. To explain how NBN investigated these, I would like to introduce Alex Grime, Integrated Planning Manager at NBN.
There's a saying at NBN Co that the one constant is change, and makes for an exciting job, but it means there's a lot of pressure on us to test those changes and see what the impact is going to be and what the benefit is. So whether that change is going from this sort of hardware to that sort of hardware, or whether it's a change in architecture, change in design rules, or change in construction practices. Each of those we need to be able to test at a desktop level, quantify the benefit and make a decision as to whether to proceed with the change. So what FOND does for us is enable us to do that quick turnaround. Instead of the old design process taking a couple of months, we turn it around in a few days and we've got ourselves a result. We can quantify the benefit, put the business case together and away we go.
As you've heard from Alex and before him Luke, the role of the fibre planner has changed considerably. Traditionally, a fibre planner was a tactician who generated the design at the lowest level of detail, piece by piece, in a CAD tool. Now a fibre planner works at a strategic level, considering options both at the local level and with regard to the overall network architecture. Let's hear from Peter again to understand how these changes affected his business.
So, how has that affected my business? I haven't been as fortunate as the characters in Fringe to actually have two universes to be able to compare with or without FOND and see how the overall difference would have been in the production of the NDDs that we've done. What I do know is that we've produced over 650 network design documents covering more than 1.5 million premises, and our production time has reduced from 45 days at the start in 2011 down to now 16 days to get that network design document out. We also believe that the actual saving in material and construction activity is around about $200 per premises right across the board. So that's where we are with the process itself. The process that we are now using utilises FOND in the early stages, in the first address matching and the address management side of it. We also then have an iterative use of FOND to go through and provide the optimum design output. So we end up iterating around about 30 times. We've had some designers that have taken it up to 300 just to see if they could get it good, and we've had some designers that can punch out a design in about 9 days. And funnily enough, our best designers are not necessarily those that are the most experienced in the telecommunications industry, but they are those that are comfortable with utilising a CAD program, map info, and using the computer to design. We actually fly all of the designs with Google Earth, and people that are what I might call the younger generation of designers are very, very comfortable with producing a design very, very rapidly. Our overall schedule of producing designs meant that we had to pump out close to 50 FSAM designs per month. In order to get that 50 a month, we've been able to do that with only 60 designers rather than the 600 designers that we believe we would have needed had we had to produce these totally manually. So our overall benefits, the efficiency of the program, it is much, much more repeatable so that we can ensure that we get the same design framework right across the nation. I've got designers that are in Perth, Adelaide, Melbourne, Sydney and Brisbane, and by utilising FOND we can ensure that we get certainty in the way that these designs comply with our design process. They're very flexible designs in that we can rapidly change them. As we get information back from our duct network, the field proving activities, if we change our architecture, all of these allow us to rapidly iterate with FOND to produce the most economical, lowest cost designs. The people that we've got doing these designs, while we only needed 60 across Australia, we can now train them much easier in the computer-aided design processes. Utilising FOND means that it's quite simple to bring somebody that's very comfortable working in a keyboard and virtual environment up to producing a high-quality design in a very, very short period of time. So what it has allowed us to do from an overall perspective is to get our productivity up and ensure that the designs were not part of the bottleneck in terms of meeting our required build profile for the National Broadband Network in Australia. And with the changes in policy, as the government changes, our shareholders change, FOND allows us to be very flexible in bringing in the multiple technology mix requirements of the future.
Avoided cost has been the key to FOND at NBN. Avoiding the hire of 600 planners and avoiding miles of unnecessary duct construction. We have qualified the savings from the bottom up. First, we have measured the design time reduction from 145 days to 16 days, giving us a saving of 129 days. Using a conservative cost of $500 per person per day, this equates to $64,500 per FSAM. As Michael and Peter have explained, the avoided construction costs can reach 20%, but with conservative average of 10%, this gives us a $200 saving per premise. This equates to $500,000 per FSAM. For the 650 FSAMs completed to date, this gives a cumulative saving of almost $370 million and at a project completion saving of $2.2 billion. The total project is estimated to cost $36 billion. Where next? The success of this project has led to further operations research projects at NBN Co and other telecommunication projects in other countries. At NBN Co, the success of FOND has significantly raised the profile of operations research and led to a number of significant OR projects, including analysis of the service footprint to determine which areas will be served by fibre and which areas will be served by other technologies such as satellite, wireless, fibre to the node and high-speed internet cables. Design optimisation of the point-to-point network between fibre exchanges and fixed wireless towers. FOND reloaded with field inspection data to generate the final detailed design. Also for NBN Co, Biarri and Render Networks have developed an optimisation tool which takes the design output from FOND and generates an optimised work schedule and manages the network rollout. Outside of Australia, FOND is now being deployed in New Zealand for the design of their ultra-fast broadband project, and optimisation pilot projects are underway in Canada, the US and Indonesia. I would like to introduce the Honourable Malcolm Turnbull, an elected member of the House of Representatives who was appointed as the Australian Minister for Communications. The Australian Minister for Communications is the functional equivalent of a senior cabinet member here in the United States. As the Minister for Communication, Malcolm Turnbull is the government minister responsible for delivering the NBN project. He is also a successful businessman and a passionate technologist.
I'm Malcolm Turnbull. I'm the Australian Minister for Communications. One of my responsibilities is overseeing the construction of the National Broadband Network, which is being undertaken by a government-owned corporation, the NBN Co. This is the largest high-speed broadband network project in the world, and it is the largest and most complex piece of public infrastructure ever undertaken in Australia. The rollout of the National Broadband Network will ensure that all households and businesses will have access to high-speed broadband regardless of where they live and work in this vast land of ours. This is a formidable challenge, but we are determined to complete the project as quickly as we can and at the lowest possible cost to taxpayers so that it is most affordable to consumers. Now, given the complex nature of the project, the NBN Co required a new approach to planning and building the network. The team at NBN Co realised that they would need help from operations research and engaged Biarri to develop a unique algorithmic-based approach to planning and building the NBN. Biarri's thought leadership in operations research and its innovative approach to solving network design problems will help to deploy the NBN faster and cheaper. Biarri's use of operations research is helping NBN Co to define the most efficient network footprint, to take a consistent 80% off the network design process, to take around 20% off installation costs for network infrastructure, and increase the speed and reduce the cost of the network rollout. The expertise Biarri brings to the NBN will help ensure the efficient and successful rollout of Australia's largest infrastructure project.
The NBN is a significant project for all Australians. Today, we have described the design and construction challenges that face the NBN, and we have shown how operations research allows NBN Co to realise design savings of $258 million and construction cost savings of $2 billion. Moreover, it is likely, without operations research, the NBN would not have been completed in the planned timeframe, and for decades, 22 million Australians would have been denied the economic, social and health benefits of high-speed broadband connections. Operations research at the NBN is truly the wonder from down under. Thank you for your time.